Hi, this is Minho, and I'm going to talk about dynamic inertial pulsar. Human pulse estimation with first IMU. It is estimating accurate and full body human pulse using only a small number of IMUs. It is robust to occlusion and lightning change, but it introduced ambiguity in unobserved joint rotation due to scarcity of IMU. In the previous research, acceleration data is underutilized due to unstableness, and they neglected spatial relationship between body parts. Also, scarcity of real IMU data and gap between virtual and real domains make it harder. Therefore, dynamic inertial pulsar solves those challenges by following methods. First, two-stage pseudo-velocity regression. Second, part-based modeling over three regions. Third, training data unified across skeleton formats. The author introduced two-stage pseudo-velocity regression architecture. In the stage 1, velocity regression network takes IMU orientation and acceleration as input and predicts the pseudo-velocity V hat. In the stage 2, pulse regression network then uses V hat, the original IMU data, and the initial pulse theta 0 to find out the pulse of joint without IMU. By combining both acceleration and orientation information in these two stages, we significantly improve pulse estimation accuracy. Second, also illustrated part-based 3D human dynamic design. They split the 6 IMU sensor into 3 regions, torso, upper limbs, and lower limbs, while also feeding all sensors into a global feature extractor to produce a good context vectors at the global. For each region, velocity regression network predicts region pseudo-velocity, and pulse regression network then predicts joint rotation in their region. Final loss is the combination of all region losses. This part-based decomposition, combined with global context, captures dependencies between neighboring joints and global motion, significantly improving the accuracy of distinguishing similar motion in different posture. Finally, the author introduced training data unified across skeleton formats. To align the two skeletons, they removed redundant torso joints, ensuring one-to-one mapping between XSense and SMPL bones. They combine XSense dataset with real IMU sensor data and SMPL dataset using virtual IMU data into the training. This unified dataset let us overcome the scarcity of real IMU recording and narrow the virtual to real domain gap, resulting in more robust and generalizable pulse estimation. The top row shows a qualitative comparison for a hand-line sequence. TIP and PIP struggle to capture subtle pulse nuance, while dynamic inertial pulsar closely matches the ground truth by effectively leveraging acceleration data. The bottom plot is a box plot of SIP orientation error across methods. You can see that dynamic inertial pulsar not only has the lowest median error, but also pure outliers compared to transpose, TIP, and PIP. These results demonstrate that our approach achieves better performance than other baselines. They also visualize the impact of their two key designs, pseudo-velocity regression and part-based modeling, on overall leg orientation error over time. The green curve is orientation error of model trained without learning velocity, and the blue curve is orientation error of model trained without part-based modeling. Lower dynamic inertial pulsar is orange. You can set the dynamic inertial pulsar makes smaller error than green and blue curve. This figure clearly shows that learning pseudo-velocity and modeling body parts separately are both essential for accurate, robust human pulse estimation. In conclusion, the author introduced dynamic inertial pulsar. It utilized two-stage pseudo-velocity regression to fully exploit acceleration data and part-based modeling to capture local joint dependencies. Also, it used unified training data to bridge the virtual to real gap. As a result, it achieved up to 19% error reduction over prior sparse IM method. Thank you for your listening.